When a pedestrian strikes a solid surface, they perform a physical transfer of kinetic energy. The mass of the human body, accelerated by gravity and locomotion, applies an immediate mechanical load into the ground material. In a quiet hallway, the resulting energy transfer is negligible, but in a major transit hub, an airport concourse, or a commercial shopping mall, that physical impact is multiplied by hundreds of thousands of footsteps every single day. From an engineering perspective, this represents a massive mechanical output, yet the physical architecture of our walkways is totally inert. All of that kinetic force simply dissipates into the surrounding environment as useless heat and microacoustic vibrations. At the exact same time, the facilities housing these pedestrians continuously draw massive amounts of grid electricity to power their peripheral systems, running corridor lights, environmental sensors, and localized charging stations. Modern public infrastructure rests directly on top of a continuous, high-volume kinetic energy reservoir, yet it remains entirely dependent on external power stations to function. Because public spaces rely exclusively on the main electrical grid, their peripheral edge devices have no localized renewable backup. If the connection drops, the entire space goes dark. Pulling from centralized fossil fuel-driven power plants to maintain continuous, low-wattage systems, like LED fixtures or temperature monitors, forces electricity to travel over long transmission lines, incurring significant voltage loss along the way. This setup also creates a secondary failure. The physical floors are data blind. Because the walking surfaces are inert materials, facility managers have no native embedded mechanisms to track actual footfall patterns or accurately map how humans move through their spaces. The conventional model for public infrastructure operates under a dual handicap. It requires a constant, inefficient supply of external power, and it lacks the granular, local intelligence required to optimize it. We can solve both the power deficit and the data deficit by integrating an IoT-based kinetic harvesting system directly into the flooring. This system utilizes a dual-stream architecture. As a pedestrian steps on a surface, the underlying hardware mechanically compresses to generate local electrical power, while simultaneously triggering a digital sensor to capture high-resolution telemetry data. This architecture targets small, distributed edge devices, decoupling them from the grid by turning the walkway into a localized microgrid. To understand how this works in practice, we need to reverse engineer the architecture of a kinetic tile, tracing the pathway from the initial physical impact all the way to cloud storage. Capturing mechanical footfall requires precise electronic conditioning to translate a chaotic physical impact into a stable, localized information network. The first requirement is capturing the raw physical event and converting it into electrical and digital signals. This schematic maps the input layer. Footsteps compress the piezoelectric array, generating an alternating current. This waveform is wildly erratic, spiking violently. To capture reliable data, we introduce a parallel IR sensor. The footstep interrupts its beam, generating a clean, binary on-off signal. A heavy work boot and a child's sneaker generate different electrical spikes in the piezo crystals. If we relied on those power spikes to count foot traffic, the data would be compromised. Running a separate infrared sensor isolates the physical presence of a step from the mechanical pressure, ensuring accurate data fidelity. The input layer effectively splits a single footstep into two usable streams, a chaotic burst of raw AC power and a precise binary digital trigger. Raw, erratic AC spikes are dangerous to microelectronics. Feeding that direct piezo output into a microcontroller or battery would damage the internal components. Looking at the schematic, we route the raw signal into a bridge rectifier. The rectifier's diode configuration forces the alternating current into a unidirectional flow. It takes the negative valleys of the AC waveform and flips into positive peaks. The current flows unidirectionally, but the voltage amplitude still ripples. It remains too unstable for sensitive storage. We route the signal into a voltage regulator. This component shears off the peaks of the bumpy waveform, flattening the electrical output into a straight line. By smoothing out these fluctuations, the regulator guarantees that the voltage remains stable, regardless of how fast or slow people are walking on the tile. With the power fully conditioned, it safely deposits into a 12-volt storage capacitor or battery. Power conditioning provides the mandatory bridge between unpredictable human biology and stable digital hardware. With DC power stored and binary IR data streaming in, The system requires a central logic controller to manage both resources. We introduce the Arduino Uno. The data feed from the IR sensor and a power monitoring line route into the board. The microcontroller runs custom embedded C software. Every time the beam breaks, the software tallies the trigger, maintaining a precise step count. Simultaneously, the Arduino queries the storage module, continuously monitoring the available voltage levels sitting in the capacitor. Tracking captured energy against pedestrian volume transforms the raw hardware into an active data node capable of reporting its own efficiency. The Arduino evaluates the available voltage and uses an array of relays to physically distribute that stored power out to local loads. The Arduino connects to Relay 1 and Relay 2, switching power on for physical outputs like an LED bulb or cooling fan. Simultaneously, it uses an IoT link to transmit telemetry to a cloud server, populating a live dashboard with step counts and voltage yields. Pushing these metrics to the cloud allows engineers to monitor system efficiency, track power generation, and identify hardware faults remotely in real time. Mapping the precise energy generation against exact footfall volume creates actionable analytics. Facility managers can optimize their building's power distribution based on accurate human traffic models. This completed block diagram represents a fully realized smart node. It acts simultaneously as a localized power plant and a granular network surveillance tool. This top-down schematic maps how the theoretical architecture scales into the physical world. The block diagram we built forms the internal logic for a single, self-contained modular floor tile. Engineers deploy these tiles across high-traffic walkways in series parallel electrical configurations. Linking the tiles in series increases the total output voltage, while parallel connections increase the available current, optimizing the aggregate power for practical applications. The most immediate application is walkway lighting. A dense array of kinetic tiles can power overhead or corridor LED fixtures, sustaining the lights from the foot traffic of the people using the hall. That same localized output powers stationary device charging kiosks and runs environmental sensors, monitoring air quality, temperature, and structural integrity without grid reliance. Modular kinetic architecture allows urban planners to decouple peripheral public infrastructure from the main power grid. Current piezoelectric arrays prove the viability of kinetic harvesting, but their energy yield serves as a baseline for future optimization. The next iteration relies on hybrid energy systems. By engineering dense mechanical enclosures, developers can layer piezoelectric arrays, triboelectric static generators, and electromagnetic induction coils into a single tile. Combining these capture methods into one coordinated mechanism ensures that every fraction of a joule from a physical footstep is extracted, increasing the total yield available for edge devices. On the software side, integrating machine learning algorithms directly into the IoT cloud allows the system to analyze historical footfall patterns. The AI can then route stored energy to specific sections of a facility based on predicted occupancy. Scaling these networks across transit hubs and airports creates a distributed power layer, providing a secondary, localized energy source for essential public electronics. Human locomotion represents a consistent, unexploited mechanical resource. Kinetic harvesting provides the technical framework to capture that movement, providing reliable, off-grid power for the sensors and lighting that define smart infrastructure.